There's one more piece of terminology, one more concept that we should talk about before we move on, and that's the idea of a type. We've talked about values, values can be numbers or booleans or strings or whatever, representing concepts either abstract or out there in the real world. But we can think of these values as being grouped together into collections of values that are similar. So, for example, we can put together a type of numbers, and they're all the numbers have in common the fact that we can do the same things to them. We can add them, we can multiply them, and so on. Um, with strings, for example, we can't add strings, but what we can do is join them together. We can split them, we can find their length, and so on. So there's a collection of things we can do to strings that's different from what we can do to numbers. And lists of collections of objects, we can build lists, we can merge two lists together, we can sort them into ascending order, and so on. So when we think of programming languages, we often think of those languages as being type aware. And languages, and Haskell, the language we're learning, we will see that that is indeed the case. If we try and add a character, the character 3, to the number 2, the system will be able to see, without trying to do the addition, will be able to see that there's something wrong because you're trying to add something, a character, to a number. Normally what we can do is add numbers to numbers. And so the system can tell us, no, you've made a mistake. You're trying to do something that the types of the objects, the values, won't allow you to do. And there's an important distinction here between um, languages like Haskell and other languages like Erlang I talked about earlier on. So Haskell has the nice property that without running the program, indeed as you write a program, it's possible to check whether the program you've written conforms with the types of the language. So if you try to write something like 2 plus the character 3 in your program, before you try and evaluate it, the system can say, no, hang on, there's a type error there. You've tried to add a character to a number. And it will tell you where the problem is, and so give you a chance to fix that problem. Other languages like Erlang and Lisp won't. They'll be silent until you actually run the program, and in that case, you'll then get a message. Oh, you've tried to add a character to a number. Whoa, that won't work. But you only find that out when you run the program rather than when you write it. And so strongly typed languages give you type errors early as you write a program, whereas weakly typed languages only tell you when the program's run. And you can imagine, in terms of writing programs, getting your programs right, it's better to know early that you have a type error. So many people prefer to use a strongly typed language, as we'll be doing in this course, rather than a weakly typed one. So that's an important distinction. A crucial point, therefore, is all functions in Haskell have types, and all those things can be checked as we write the programs in Haskell. So an example is the multiplication has a type. It takes two integers and returns an integer, and we write that in this terminology here: integer, arrow, integer, arrow, integer. So the first two integers are the types of the inputs, and the last integer is the type of the result. And similarly, and the way we write in Haskell is of type, is we write colon, colon. So we here say double is of type integer input to integer output. So that's the way we write it in Haskell. And what we'll find is that every time we write a definition, something like double of x equals 2 times x, we will also write its type. Now, in fact, we'll see we don't have to write its type because the system can tell us what type it has. Haskell has what's called type inference. But, and this is, people disagree about this. Some people say, because if the system can tell us what its type is, why do we bother writing it? I would say it's the most important piece of documentation that you can think of. Without knowing the type of your function, you know nothing about it. So why not write it down so that your program contains what the type is? And also that gives you a chance, if you somehow got the type wrong in your head, the system can check that your intuition about what the type is indeed correct. So I would say, and I'd advise you always to write the type of the function that you're defining as you define the function. Now I've talked about lists and strings and so on. Haskell provides built-in types, integers, floating point numbers, strings and so on, and it provides ways of combining those together. So we can build lists of integers, or lists of floats, or lists of floats. So we can build all those different types using the facilities of Haskell. And we can also build records and a number of other different kinds of collection types. But more importantly, and what you'll find we'll be doing a lot of as we progress, is we can define new types for ourselves. So for example, we can define a type called shape of geometric shapes. So some of our programming in Haskell is designing types over which we write functions to perform certain sorts of operations. And we'll spend a lot of time, as I say, thinking about different ways of defining types, using built-in and user-defined types, and combining those together. And one of the things that we will make a functional language particularly distinctive is the fact that we can have functions as values themselves. So we can pass functions as arguments to other functions, or get functions back as a result of a function application. And we'll spend quite a bit of time later in the course talking about that. And so Haskell has a very expressive, so the types are there to help us. They're like guardrails. They help us not to make mistakes in writing programs, and Haskell checks that as we write the program. So they're, in a sense, they're a restriction, but Haskell does have an expressive set of types and ways of forming types. So it allows us to write a whole lot of different kinds of things. So I think this is at least as important is getting types right before you start writing definitions. And indeed, what I wanted to finish this little section with is to talk a bit about type-driven design. And the way that we tend to write things in Haskell is that we first of all define a type like shape, and then we think about what types of functions we want to write over shapes before we start writing those functions themselves. We let the type of the function drive the design of that function. So for example, we've got shapes, define that somehow. One of the first things we want to do is write a function that takes a shape and returns the area of that shape, which would probably be a floating point number. So we can write that type down, and then we can think, let's roll up our sleeves and define that function itself. So this is the types drives the design of the functions. So values divided into types like numbers, integers, floating point numbers, strings, and compound types built from other types like lists of strings, and function types. But as I say, we'll discover the different ways you can form types as part of the way that the course is structured, looking at different ways of building types and how we define functions over those.